Cloud storage is one of those services that feels deceptively simple because it often looks like an endless folder where you can drop files and retrieve them from anywhere. The risk is that this convenience is built on shared infrastructure, shared services, and shared operational patterns, which means a mistake in configuration can scale into a very large exposure very quickly. When resources are shared, you are relying on isolation boundaries that are mostly invisible, and you are also relying on your own choices about identity, permissions, and data handling. The most common failures are not exotic cryptographic breaks, but ordinary human assumptions about who can access something and whether a setting is private by default. If you treat cloud storage like a local drive with a network cable, you will eventually be surprised by how far the blast radius can extend. Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. The organizing concept that keeps the conversation honest is shared responsibility, which is the split of duties between the cloud provider and the customer. The provider is responsible for the security of the underlying cloud, meaning the physical facilities, hardware, core networking, and foundational service operations that customers do not directly touch. The customer is responsible for security in the cloud, meaning the way identities are managed, permissions are granted, data is protected, and service configurations are applied to meet the organization's risk and compliance needs. The tricky part is that the boundary shifts depending on the service model, the provider's features, and the customer's choices, so you cannot assume a single universal split. A mature approach is to treat shared responsibility as a control mapping exercise, where you explicitly identify which party provides which control and what evidence demonstrates that it is actually working. Because cloud storage is multi-tenant, tenant isolation is a core protective mechanism, and it is one of the reasons these platforms can safely serve many customers at once. Isolation refers to the provider's ability to keep one tenant's data and operations separate from another tenant's data and operations, even though they run on shared infrastructure. That provider isolation is necessary, but it is not sufficient for your security outcomes, because your exposure often comes from your own configuration choices within your tenant boundary. In other words, isolation helps prevent other customers from casually crossing into your environment, but it does not prevent you from accidentally opening your own doors to the public internet or to overly broad internal access. Treat tenant isolation as a baseline guarantee that enables cloud computing, and treat configuration discipline as the thing that determines whether your own data remains properly contained. Identity control is the practical gatekeeper for cloud storage because access is almost always mediated through identities, roles, and permissions rather than through network location alone. Identities include human users, service accounts, application identities, and workloads that act automatically, and each of those identities needs a clearly defined scope of authority. Roles are typically the way you group permissions into job-aligned bundles, and permissions define what actions can be taken, such as reading objects, writing objects, listing contents, or modifying configuration. The security objective is least privilege, meaning each identity receives only the permissions needed for its purpose and no more. But the operational challenge is that storage access tends to be shared across many systems and workflows. When you design identity controls well, you reduce the chance that a single compromised credential becomes a universal key to your data stores. One of the highest impact failure modes in cloud storage is misconfigured bucket and share settings that expose data publicly. Storage services often have controls that determine whether a container, bucket, share, or directory is private, internal, or publicly accessible, and those controls can exist at multiple layers. You can have a bucket that is intended to be private, while individual objects are made public, or a bucket that is accidentally configured for anonymous listing, which then enables discovery of sensitive data, even if the data itself is not widely linked. Sometimes exposure happens through policy language that grants broad access to a large group, or through inheritance models that apply permissive rules to many resources at once. The pattern is consistent. A single, overly broad setting can create an external interface to internal data, and cloud scale means that exposure can be immediate and wide. Encryption at rest is a foundational control for stored objects, but the details matter because encryption can be provided in different ways with different key management implications. Many providers offer server-side encryption by default, which means the platform encrypts data before writing it to disk and decrypts it when authorized access occurs. Providers also offer managed key options, where the provider handles key storage and protection, and this can be sufficient for many risk models because it reduces operational complexity while still providing confidentiality against underlying media exposure. There are also cases where encryption is applied at the application layer, meaning data is encrypted before it is uploaded, which can provide stronger separation from platform operators but can introduce key management and usability challenges. The key point is that encryption is not a single checkbox, because your threat model determines whether you need stronger key separation, stronger auditability, or stronger control over when and how decryption occurs. Customer-managed keys raise the control level by putting key lifecycle decisions more directly under the customer's governance. With customer-managed keys, the organization defines key creation, rotation expectations, access policies, and sometimes even the hardware security boundary that protects the keys. Rotation is important because it limits the impact of long-lived key exposure and aligns with compliance expectations. But rotation must be designed to avoid accidental service disruption or data inaccessibility. Access control separation is a major benefit when done correctly, because the people who can administer storage should not necessarily be the same people who can administer keys, and that separation reduces the chance that a single compromised administrator account can both access encrypted data and control the keys that decrypt it. When key management is treated as its own privileged domain, encryption becomes a meaningful barrier rather than a symbolic feature. Logging is the memory of your storage environment, and without it, you are left with assumptions when something goes wrong. Storage access logs record who accessed what, when it was accessed, and what action was taken, which is essential for investigations and for detecting misuse. Configuration change logs record when policies, permissions, public access settings, or lifecycle rules are modified, and these changes often explain exposures more directly than access logs do. The challenge is that logging must be enabled intentionally, routed to a protected destination, retained long enough to support investigations, and reviewed with enough fidelity to be useful. When logs are incomplete or stored in the same place that is under investigation, adversaries and careless insiders can erase or manipulate evidence, which turns a security event into an unresolved mystery. Data lifecycle controls are a security topic, not just a cost optimization topic, because they govern how long data exists, how many versions remain, and how deletion is enforced. Versioning can protect against accidental overwrites and some forms of destructive behavior because it preserves prior object states, but it also increases the amount of data that exists and therefore increases the amount of data that can be exposed. Retention controls can prevent premature deletion and support legal and business requirements, but they also create a requirement to protect data that must remain available even when it is no longer actively used. Deletion controls are often misunderstood because deletion in cloud storage can be logical rather than immediate physical removal, and the actual process may involve delayed purging and replicated cleanup. A well-designed lifecycle policy balances availability needs, legal requirements, and exposure reduction, while ensuring that operational processes do not unintentionally preserve sensitive data indefinitely. Secure sharing is one of the most common reasons organizations use cloud storage, and it is also one of the easiest ways to leak data when convenience takes over. Time-limited links are a powerful pattern because they allow temporary access without permanently broadening permissions, but their safety depends on the strength of the token, the duration, and whether the link can be forwarded beyond the intended recipient. Scoped permissions matter because sharing should grant only the actions required, such as read-only access to a single object rather than listing an entire container or writing new content. The security posture improves when sharing is treated as an explicit decision with an expiration, an audit trail, and a clear purpose rather than as an informal habit. When you combine time limits with narrow scope and strong authentication where possible, sharing becomes a controlled capability instead of an unmanaged risk. Malware scanning and content validation are increasingly important in storage environments because storage is often a transit point for user-supplied or partner-supplied content. Uploads can contain malware, embedded scripts, macro-enabled documents, or crafted files designed to exploit downstream consumers such as parsers, viewers, and analytics pipelines. Scanning helps detect known malicious content, but content validation is just as important because many attacks rely on tricking systems into treating one type of content as another, such as hiding executable content inside a file that appears benign. The goal is to prevent storage from becoming a distribution mechanism for malicious payloads and to reduce the risk that internal systems ingest dangerous content automatically. When you design upload workflows with validation, scanning, and quarantine patterns, you reduce both security incidents and operational disruption from contaminated content. Backup and replication features improve resilience, but they also expand security considerations because copies create new access paths and new places where data can be compromised. Backups must be protected with access controls that are at least as strong as the primary storage controls, and ideally stronger, because backups often become a last resort target for adversaries looking for high-value data. Replication can create additional regions or environments where data exists, which increases the number of identities and services that might have access and increases the complexity of ensuring consistent policies. Replication also affects incident response because containment may require you to isolate or suspend access across multiple copies simultaneously, and restoration planning must account for which copy is authoritative. Resilience features are valuable, but they must be governed as part of the security design so they do not quietly create uncontrolled data sprawl. Monitoring is the discipline that turns logs and telemetry into timely awareness, and in cloud storage, it often focuses on anomalies that suggest misuse or compromise. Large or unusual download patterns can indicate data exfiltration, especially when they occur from unexpected identities, unexpected locations, or at unusual times. Unusual deletion patterns can indicate destructive activity, whether malicious or accidental, and those patterns should trigger rapid containment and validation of versioning and backup readiness.
Access bursts can also reflect credential abuse, where an adversary tries to enumerate and retrieve many objects quickly before detection, and this is where rate-based alerts and behavior baselines become useful.
Effective monitoring depends on clear definitions of what normal looks like for a given storage workload, because storage usage patterns vary widely across business functions, and generic thresholds often create either noise or blind spots. Cloud storage security ultimately rests on disciplined control of identity, disciplined configuration of access settings, and ongoing oversight that detects drift and misuse. Shared responsibility means you can rely on the provider for foundational protections, but you remain accountable for who can access data, how it is shared, and how it is monitored. Tenant isolation provides a baseline separation from other customers, but it does not protect you from your own policy mistakes or overly broad permissions. Encryption, key management, logging, lifecycle rules, and monitoring all work together, and weakness in one area can undermine the confidence you have in the others. When you treat storage as a security-sensitive service rather than a neutral utility, you build systems that scale safely without relying on luck. The result is not only fewer exposures, but also a clearer ability to prove control, respond to incidents, and keep shared resources from becoming shared risk. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.